Last time we talked about how you can use a congruence statement to show different parts of the triangles corresponding to a triangle that it's congruent to. Today we're going to talk about what we call triangle congruence proofs. These are ways that we can show that two triangles are congruent to one another without having to show every single angle and every single side have corresponding parts that are congruent to one another. Alright, so we said triangles are congruent if all of their corresponding parts, their angles and their sides, are congruent. Now, the property of what we call triangle rigidity states that if all the side lengths of a triangle are given, the triangle may have only one shape. Now, this property allows us to use shortcuts in order to prove that triangles are congruent. When I say shortcuts, I mean that you do not have to have all three sides and all three angles of two triangles in order to show that they are congruent to one another. We're going to go through all of these shortcuts. So the first is what we call side, side, side. So if three sides of one triangle are congruent to three sides of a second triangle, then the two triangles are congruent. Here's a picture of an example, and we would be able to state that triangle ABC is congruent to angle FDE. Now you'll notice here that we did not say anything about the angle measures. However, that doesn't mean the angle measures are not equal to one another. It just means that we do not need to know what the actual angle measures are in order to declare that these two triangles are congruent to each other. Next is what we call side angle side. This says that if two sides and the included angle of one triangle are congruent to two sides and the included angle of a second triangle, then the two triangles are congruent. Now you'll notice that the way I've stated it here is side angle side. This indicates that the angle is the one that's formed by the two sides. That's what we call the included angle. Here's an example. So you can see here, angle A is the included angle because it is the one that's formed by the blue and the green sides of the triangle. Same with angle E. It's the one that's formed by the blue and the green sides of the triangle. Okay, so given that information, given those two sides and the included angle, we can use the shortcut way and say that these two triangles we know are congruent. So we can say that triangle ABC is congruent to triangle EFD. Now this is just to be clear so that you have it down for yourself in your notes. An included angle is an angle that's formed by two adjacent sides of a polygon. So in this case here, angle B is the included angle that is formed by sides AB and CB. The next shortcut is what we call angle side angle. This says that if two angles and the included side of one triangle are congruent to two angles and the included side of a second triangle, then the two triangles are congruent. Here's an example. So instead of talking about an included angle, now we're talking about an included side. That means this is the side that is in between those two angles. In this case, you can see that side AC is the side that is in between, or the included side, of angle A and angle C. Same with triangle DEF. We have DF being the side that is between angle D and angle F. So this shortcut says that if you have two angles in the included side congruent to two angles in the included side of the other, then you can state that these two triangles are congruent. So here we can say that triangle ABC is congruent to triangle DEF. The next shortcut is what we call angle angle side. This says if two angles and a non-included side of one triangle are congruent to two angles and the corresponding non-included side of a second triangle, then the two triangles are congruent. Now notice how in this case we're stating it as angle angle side rather than angle side angle, which was the last one. This is because this side is the non-included side. It is not the side that is between those two angles. However, you want to be sure that that non-included side, that's the one that you're looking at, is the correct corresponding non-included side. It will be attached to one of the congruent angles. So here's an example. We have GHJ, which is congruent to KLM. Now you see here that G and J, those two angles, are congruent to K and M. Now the non-included side would be HJ. It's not the side that's between angle G and J, but notice how it is the one that is connected to angle J. Now angle J corresponds to angle M. So now you can see how LM on the other triangle is the corresponding non-included side to HJ. So now if we have that information, we can state that triangle GHJ is congruent to triangle KLM. Okay, our last shortcut is called the hypotenuse leg, or the HL. So this says if the hypotenuse and a leg of a right triangle are congruent to the hypotenuse and leg of a second right triangle, then the two triangles are congruent. So this is what we have here. Now this only works with a right triangle. You'll notice otherwise, if this helps you to remember, you would be saying that this would be angle side side, which if you wanted to abbreviate, comes out to be a very unfortunate way of abbreviating it. So since that also doesn't work, instead of saying angle side side, it's a right angle, and then a side, and then a side. Now it's easier, since this has to be a right triangle, we can just simply say that you have a hypotenuse corresponding to another hypotenuse, a leg corresponding to another leg in a right triangle. So in this case, we would say that triangle ABC is congruent to triangle DEF. Let's take a look at some examples and see if we can identify whether or not we can show that some triangles are congruent and which shortcut, or in other words, which theorem we would use to do so. Alright, so here's our first example. We see here that CD corresponds to AB, AD corresponds to CB, and then we actually have AC, which is just the same for both triangles. So in this case, you can see that we're showing we have three sides of a triangle congruent to three sides of the other triangle. So we would first want to list the theorem that we're using. Well, we're using three sides, so this would be side, 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 or you can abbreviate that as SSS. And then now we want to list out the corresponding congruent parts. So what you're going to do is you're going to write down the set of sides, the other set of sides, and then the third set of sides. So I'm going to write S to represent the set of sides that I'm going to show. So the first set of sides, AB, corresponds to CD, AD corresponds to BC, and AC corresponds to AC. Let's look at the next one. Right away, when you see a right angle, you probably want to check to see if hypotenuse leg is the one you want to use. We do see that we have a hypotenuse in one triangle congruent to the hypotenuse in the second triangle. We also see that these two triangles share a side, which happens to be the leg. So we are definitely going to use the hypotenuse leg theorem here. And we want to list off the corresponding congruent parts. Now, because we're working with the hypotenuse leg, they have to be right triangles. So we'll start with that. Angle BCD and angle CBA are right angles, so therefore we have right triangles. That means the hypotenuse, H, AC, is congruent to BD. Then for the leg that it shares, we can write that BC is congruent to BC. Let's look at the next one. So in this one, we can see that we have a set of sides that are congruent. We have a set of angles that are congruent. Now we need at least one more piece of information. Now you can see here that at T, we actually have some vertical angles. So angle STW and angle VTU, those are vertical angles, and vertical angles we know must be congruent to one another. So since we have two angles congruent to two angles in the other, and the included side congruent to the included side of the other, we can use angle side angle. Now we write down the corresponding congruent parts. So for angles, we can start off with angle SWT congruent to angle TVU. Now if you wanted to, you could absolutely just simply say angle W and angle V. In this case, that's not ambiguous. And then the sides, that would be WT congruent to VT. And then the vertical angles. Now this one you don't want to say that angle T is congruent to angle T. That's very unclear which angle you're referring to. So here you'll want to use three letters. So angle STW is congruent to angle VTU. All right, the next one. Here we have, it looks like two sides congruent to two sides of the other. And we also have the included angle congruent to the included angle of the other. So here, we're going to use side angle side. Now we list off the corresponding congruent parts. We'll start off with a side. So we can say AC is congruent to CD. Angle ACB is congruent to angle DCE. Again, here you don't want to simply say angle C is congruent to angle C. That makes it very unclear which angle you're referring to. And then we have one more set of sides that we have to list off, and that would be BC is congruent to CE. All right, our last example. This one, it looks like we have angle K and angle M congruent to each other, side KJ with side MN, and we still need at least one more piece of information. In this case, again, it looks like we have some vertical angles to work with. So angle KLJ is congruent to angle MLN because vertical angles are congruent. So in that case, it looks like we have two angles and a non-included side congruent to the two angles and the non-included side of the other. So let's go ahead and list off those angles and the non-included side. So the first set of angles, angle KLJ congruent to angle MLN because they are vertical angles. The next one, you could say angle K and angle M, or you can say angle JKL and angle NML congruent to each other. And then the non-included side, JK is congruent to MN.